humanity has known for centuries that there is a connection between the tides and the phases of the moon. So let's clearly define the tides. You can think of it as the water coming in and out throughout the day. Right? This is one of the more extreme examples, one of the greatest tidal differences between low tide and high tide. Over the span of 12-ish hours, this whole area, about 15 meters in depth, will be completely flooded, and then 12 hours later, empty again. Right? So people have been observing the tides coming in and out, and they noticed that the height of the tides would change depending on the phases of the moon. So if you ever hear of folklore, say like werewolves, lichens, and such, which where they came from, where they originated from, was this association of the moon's effect of us on Earth. So let's move on and let's actually explain why the moon causes the tides. And I'll start off with a little bit of a question. Let's see if this makes sense. Which diagram is the best representation of the tides, right? You'll have the moon, you'll have the Earth, and then you'll have the oceans, the bodies of waters of the Earth. So which one makes sense? Go ahead and pause, think about it, come back. A cannot be correct. There are two tides a day, right? So imagine you're an observer here on Earth, right? Right, you're in high tide at this point, and then continue on with your day. 12 hours later, you'll be at low tide. Then another 12 hours, so one day from the initial, you finally came back to a high tide, which is the complete opposite of what we see today. We see that as the day continues, you start off with a high tide, and about 12 hours later, you'll be in a high tide again. So I imagine a lot of students picked answer A because we just talked about all the gravitational stuff. We've talked about how the moon has a gravitational pull, and we want to logic and think that the water's being pulled towards the moon. So can gravity alone explain this tide that's coming out? This one we're pretty solid on. Gravity's stretching the water towards itself, but how the heck can we explain this? Let's construct what we're going to eventually dub the tidal forces by beginning with the gravitational force that we've studied so far in this section. So the moon has a gravitational pull on the Earth, and the gravitational force is an inverse squared law. So the further away from the moon you get, the weaker the force is. So you're going to have a strong force on the point closest to the moon, and it gets weaker and weaker as you get further and further away from the moon. So, yes, the tides are a consequence of gravity. Think of it as like a spring model. Here's our spring system. You have the section that has the strongest pull on it, middle pull, and the weakest pull. And as the moon stretches the Earth out, this one will accelerate a lot. This will have a strong pull, pulling away. This one will move a little bit. And this one, relative to the net acceleration, will have gone in the opposite direction. Right? Now, I know that's confusing, so let's try and be specific. And we're going to have a lot of pictures, a lot of diagrams to try and net this idea here. So, the center of the Earth and the moon orbit like point masses. Remember, when you talk about the center of mass, where can you calculate all the forces on someone? You say they all act from the center of mass. So there is this net acceleration. All of the forces of the moon here, 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 here. Add all those up, and you'll get a average acceleration stretched out by the center of mass. So the center of mass will have this net acceleration. Well, there's still an acceleration from the edges that are closest and furthest. So when you correct for the center of the Earth moving towards the moon and the weaker force of one side and the stronger force of the other, when you correct for that, you'll create the tidal bulges. The moon splitting, separating the Earth apart. On this top picture, we're going to draw pictures of the gravitational force of the moon on different segments of the Earth. Now, if I was to take every single one of these, add them up, I would find the average force. There it is. There's the average force. Think about the center of mass of the moon pulling on the center of mass of the Earth. So our definition of the tidal forces is going to be the force at every point on the Earth minus the average force, right? So let's go to another picture to try and help visualize this. Let's look at the big picture. So I'm only drawing the forces on the perimeter of the Earth, and I've drawn a lot more. On the edges closest to the moon, we're going to have the biggest, strongest force. On the edge furthest away, the weakest. And then in black here, I have that average force again. Now, tidal force, by definition, is this crazy difference. Now, I know this isn't very illustrative. I know this is kind of weird to comprehend, but remember, the center of the Earth is getting dragged away, while this side isn't getting dragged as much. And that's the difference. There is a differential force. Strong force on the Earth here, weak force over here. And that becomes this stretching effect. Now, let me try and draw on this to help visualize what we're talking about. So I'm going to look at this point here. The gravitational force of the moon on the Earth there will be going off this direction. Now, if I draw the average force that we're subtracting out, the average force is going off that way. And it's the combination of these two. Imagine being pulled on in a tug-of-war game. You have a little bit pulling you down in the purple direction. You've got one tug-of-war rope pulling you in the purple direction. You have another tug-of-war rope pulling you in the black direction. Well, with these two ropes tied to you, pulling on you, which way are you going to go? Well, it's going to be the net between them. You end up going this direction. You get yourself pinched. All right? So once again, the idea, what you're trying to think of here is that there are these competing tugs on you. One tug going this direction. Another one from just all the other mass around you pulling this way. And the fight between these two tugs ends up having this net force pulling you down. And definitely think about this game of two ropes and this tug-of-war game pulling on you. Well, this tug-of-war game is happening at every point around the planet. So instead of drawing all this complex tug and pull, let's just look at the net effect. And we'll find that, yes, here are the tidal forces of the moon on the Earth. And we see the wonderful tidal bulges. The parts of the Earth closest to the moon get stretched out, so you'll have a high tide here. The parts of the Earth far away from the moon are also getting stretched out. So even though the gravitational pull of the moon here is to the right, the combined effect of the moon pulling the water here versus pulling the center of Earth stronger leaves this stretch of the Earth elongated out. And thus we get our tidal bulges. On these sides of the Earth, you get that pinching effect. So you are compressing and stretching the Earth by tidal forces. One last thing to notice on this picture, look at the length of the tidal forces on the close side to the moon versus the far side. Now, this image is way off scale. To get this to be in the proper scale, this moon would have to be about 12 times further away. It'd be way off the screen. So, yes, it is true that the high tide closest to the moon will be slightly bigger than the high tide on the opposite side of the Earth. They're going to be a lot closer. We're talking millimeters in difference on a given day. So to put this tidal bulge and a bit more to scale, the moon is way off screen here. So this would be the high tide closest to moon, high tide furthest away. And they're much closer in size. Yes, there is a slight discrepancy. There is a slight difference. This one will be bigger, but it's a tiny difference. And that's just due to the distance between the Earth and the moon and the size of the Earth. Emphasis here. Here are your tidal bulges. You get high tides here and low tides here. So using this picture, let's talk about Earth rotating underneath this tidal bulge. Imagine you're right here experiencing high tide right now. Now, if you recall, the Earth is rotating. In this picture, I'll have it rotating in this direction. So you're currently in a high tide. The Earth will rotate. And at that later time in the day, about 6 hours later, you will be at low tide. So all that water has drained out. And then you can imagine rotating again, and you'll get to high tide once again. And keep going, repeating this process. Now remember how one face of the moon is what we said was tidally locked to the Earth? No matter where the moon is in its orbit around the planet, it's always looking the same direction. That's due to these tidal forces. These tidal forces are creating what we'd call this kind of drag on the moon and on the Earth, causing them to get locked in towards each other. Additional, making this tidal problem even more complex. Earth, due to its own self-gravity, is trying to be a nice perfect sphere, but the tidal forces of the moon is stretching us out. So we're no longer this perfect sphere anymore. We have these tidal bulges stretching the mass out. And it's not just the oceans of the Earth that's being stressed out. The physical rock, the material, our tectonic plates, they are also being stretched ever so slightly. So this combination of factors, these things stacked on top of each other, well, these distortions are causing, say, the lunar month. Think about this. A little segment of the Earth is ever so slightly closer to the moon, and it's going to be not quite aimed at the moon, because you have to think about, well, Earth's rotating this whole time. So our bulge doesn't exactly aim towards the moon. So you have a slight mass here pulling on the moon, slowing it down a little bit. Now, it's not much. Over the course of a century, the lunar month will have increased by about 0.014 seconds. So this is a small, gradual effect, but over the eons, this will be measurable. Let's go ahead and look at some further nuances about these tidal forces. Here we're looking at an example of a lunar tide. And you notice I haven't drawn the tide to be pointing directly at the moon. It's off a little bit, rotated a little bit. Well, what's happening? The Earth is rotating. The Earth is rotating around, doing its normal 24-hour cycle. And there is this rotational drag. We sometimes call it rotational friction. You have the lunar tide trying to stretch the planet out this way, and the Earth is rotating along, so you have that rotational force, a rotational drag, pulling the water, the oceans up this way. And so the tides do not aim directly at the moon because of Earth's rotation. Going even further now, the only requirement for a tide is two massive bodies. They have to have some size and have some gravitational force between them. So we've only talked about lunar tides, Earth and the moon. But it's perfectly valid to discuss solar tides. Here is the sun, and there is a gravitational force. On one side of the Earth, it's stronger than the other side. It's the exact same picture. It's the exact same mathematics to create a lunar tide. So we'd call these solar tides. And now we can talk about the combination of solar tides and lunar tides. Make it this three-body problem again. So I'll tell you now, the lunar tides are about twice as strong as the solar tides, just due to the proximity of the sun, earth, and moon. Now let's talk about what's happening to the tides at this point. What's the sun tide doing? Sun tide in this picture is going to be pointing this direction, whereas the lunar tide is the rotated direction. This is what we would call a neap tide, also called a suppression. Zooming in on this, let's look at the neap tide now. So on a neap tide, the sun's off in this direction, the moon's up there. And why call it a neap tide? Well, let's draw on here. Let's show what the sun tide is doing. The sun tide is trying to do something like this. So on these edges of the Earth, the tidal forces are going that direction. Whereas on the top and bottom, the sun tides are trying to compress the Earth. So I've got a solar tide that's stretching and compressing in the opposite orientation of what the lunar tides are doing. The lunar tides are trying to stretch here and compress here. So they're fighting, they're competing with each other when the orientation is moon this way, sun this way. And so the tides will then get suppressed. They are not as big at this time. And so we call them a neap. The tides are neaped, suppressed. Well, if they're lined up, the moon and sun, well, now what's happening? Well, the lunar tide is stretching this way, compressing this way. The solar tide is stretching this way, compressing this way. They're working together now. Now they're adding together. Thus, we'd say the tides will be bigger at this time, and you'll have a higher tide than usual. You'll have a spring tide. So one question to ask yourself right now, when we call these spring and neap tides, how many times in a year does a spring tide occur? Is it called a spring tide because it happens in spring? No. The spring just means that it's springing forth. It's more bountiful. It's a higher tide. How many times in a year are you going to have the orientation of moon, earth, and sun? Well, if the sun's over here, sun, earth, moon, this would be a full moon. There are 12 full moons in a year. So there'll be 12 spring tides of this orientation. Well, a spring tide, as you won't be surprised to learn, also happens when the moon's here as well, at new moon. So you'll have a spring tide twice a month for every new moon and full moon. Neap tides, first quarter, third quarter for the lunar phases. So these spring and neap tides happen twice a month. We constantly think about how the tides are affecting the oceans, but it's also affecting the solid parts of the Earth too. And as an example, take your hands together, squeeze them together, right? So you got a good grasp between your hands, and now start just rubbing them against each other, pushing really hard, right? As you're rubbing your hands together, you've got these forces stretching, compressing them. And what's happening to your palms? They're heating up. They're getting warm, right? So there is this tidal friction, and that can generate a lot of heat, right? If you look at Europa, a moon of Jupiter, Europa has been superimposed onto this actual image, but what you can see here is what looks like a water plume. We think Europa, while it's orbiting Jupiter, is getting such extreme tidal forces that this stretching, compressing game on the solid parts of the moon is creating enough friction, enough residual heat to create liquid waters on Europa. There's one mission that I absolutely want to see happen in my lifetime. Yes, going to Mars is high up there. Yes, building colonies, going back to the moon. But if there's one mission that I absolutely want to see happen in my life, it's sending a submarine to Europa. I want to send a robot that can land on the surface of Europa and drill down through the ice layers and get to what is potentially a liquid ocean. Because I am very certain that we'll find life there. Can't promise it. We have to go there first and find out. But in my opinion, there is definitely a high probability of organisms living in the moon of Europa, powered by the tidal forces squeezing and stretching that moon out. Now, coming back to Earth, same thing's happening, not as dramatic. The moon is no Jupiter here. But there is some tidal friction stretching the shape of a planet, and that ends up in a net effect on Earth that causes the day to lengthen. We're about 0.0015 seconds every century. We get a day that's a little bit longer. Taking this to the extreme limits, what happens when the tidal forces are too strong? Think back to Europa. There's enough friction on there that there's potentially liquid water underneath the icy, crusty surface. Well, what if the tidal forces were stronger? What if the stretching and compressing of the planet was greater than the planet's ability to hold itself together? That is what we call the Roche limit. If the tidal forces exceed the Roche limit, then that planet will literally be sheared apart. The tidal forces will be so strong they'll overcome self-gravity and rip the planet apart. When we talk about rings of other planets, we think that those are former moons that went beyond the Roche limits, had tidal forces so strong that it ripped those planets apart. And we see examples of this Roche limits acting on planets, acting on stars, even on the size of galaxies. We see tidal forces stretching and deforming galaxies, galactic sizes, beyond their possible limits to hold themselves together. So it's a very big, important concept, but the summary, the shorthand version of this, is that there is this limit to how much you can hold yourself together due to gravity versus tidal forces ripping you apart. One last example before we wrap up. If you ever have a discussion about black holes, you'll hear concepts about death by spaghettification, how you will get stretched out as you approach the black hole and be ripped apart, atomized. That is an extreme example of the Roche limit. The forces on your feet are thousands of times stronger than the forces on your head due to tidal forces, and thus you get stretched out. So in summary of everything we discussed in section 4, Newton's law of gravity says that the gravitational force is the universal gravitational constant, the mass, the product of the masses that are tugging on each other, divided by the distance between them squared. If you wanted to orbit a planet, if you want to be a satellite orbiting a planet, you need to be moving at a minimum speed. And at that minimum speed, you'll be doing a circular orbit. And that circular orbit goes as gravitational constant again. The mass of the planet you're orbiting, your mass is irrelevant. And here R would be the distance between the center of the planet and where you are orbiting. Not the size of the planet, how far away from the planet you are. Going further, do you want to get away from the planet? Do you want to, say, send a spacecraft to study Jupiter? Well, then you have to go fast enough to escape the gravitational pull. And that escape speed is a factor square root 2 times faster than the circular speed. Any speed in between these two, and you'll have elliptical orbits around the planet or sun. Anything greater than this, and you'll have what's called unbounded orbits, and they can be parabolic or in extreme cases hyperbolas, and you will launch off away from the planet. The tides are a product of gravitational forces stretched out across the planet. If the moon was over here, gravitational force closest to the moon is stronger than gravitational force on the far side of the moon. or far side of the Earth. And that combination of this differential force stretched out across the planet creates this tidal forces, where you'll have these tidal bulges and a suppression causing 2 tides a day. And then finally, you can talk about things like spring and neap tides, which are sun tides and moon tides stacked on top of each other. Sometimes they'll add and they'll cause the tides to spring up, and sometimes they'll fight, suppress, and cause the tides to be neap down. So I'll call it into this section. All right. Enjoy next time.